Welcome to the Deep Dive, the show where we really try to take a whole stack of information, cut through all the noise and boil it down to what you really need to know. We want to give you that shortcut, that essential understanding. And today, wow, we're plunging into something that's literally at the core of our electric future, the electric motor itself. I think for a lot of us, the whole idea of an electric vehicle, it paints this picture, right? This really green mobility, clean energy, no exhaust fumes, quiet driving, leaving no trace. But then you start digging just a little bit and you hear about the materials, the actual stuff that goes into these supposedly clean machines, especially the motors. And makes you wonder, is there like a hidden cost, a catch to this whole clean mobility thing? Are we maybe just swapping one kind of environmental problem or even geopolitical issue for another? I'm genuinely curious if there's a better way, a truly sustainable way forward.
That's not just a casual thought. It's actually a critical point. You've really hit on one of the biggest, maybe the biggest, challenge facing the entire EV industry right now, that reliance on rare earth materials. These aren't just, some minor ingredients. They are absolutely foundational, essential components in the most common EV motors we see today. And yeah, they come with a hefty price tag, volatile too, and a really significant environmental impact. Plus, like you said, some serious geopolitical baggage that, frankly, we can't just ignore. But here's where things get really interesting, exciting even. Zia Friedrichshafen, huge global player in automotive tech, they've developed what I genuinely believe is a groundbreaking answer. They call it the I2SM. That stands for In-Rotor Inductive-Excited Synchronous Motor. And trust me, this isn't just tweaking things around the edges. It feels like a revolutionary step, a true paradigm shift that tackles these exact concerns head on. It completely redefines what's possible for EV power.
Wow, okay. A paradigm shift? A game changer. Those are pretty bold words. And, that immediately gets me thinking, how can you really revolutionize something so fundamental like an electric motor without just, I don't know, pushing the problem somewhere else? My first reaction is always, okay, what's the catch here?
And that's exactly the kind of healthy skepticism we need. It's why we're doing this deep dive today. Our goal, our mission for you listening, is to give you that definitive shortcut. To really understand this innovative I2SM technology, we're going to unpack exactly how this motor manages to ditch permanent magnets completely, what specific engineering feats make it so efficient and surprisingly compact, and maybe most importantly, what its existence actually means for the future of truly sustainable mobility. By the time we're done here, you'll be, I think, incredibly well informed and maybe, hopefully, even a little amazed by what's possible when smart people tackle these big, complex problems.
Okay, let's definitely unpack this then. A motor without magnets. Honestly, that sounds almost impossible to me. I mean, I sort of grew up thinking magnets are just fundamental, like non-negotiable for how any electric motor works. So my first question, the one that's really buzzing around in my head, is just how? How does this thing actually work? What is the core, the fundamental difference in how it operates compared to the motors we see in most EVs right now?
That is the perfect place to start because it really gets to the heart of the innovation and why it matters so much. To really get why the I2SM is so clever, we first need to understand the problems it was designed to solve. It didn't just appear out of thin air. It's a direct answer to some very, very pressing issues in the industry. So right now, the main type of motor, the one you'll find in the vast majority of electric cars on the road, that's the permanent magnet synchronous motor, or PSM. And look, they're popular for good reasons. They offer fantastic power density, lots of power in a small package. And they're very efficient, especially across the different speeds a car needs, right? Stop-start traffic, cruising on the highway. Basically, how they work is they use these really powerful permanent magnets, usually made from rare earth alloys. These magnets are actually embedded right inside the rotor, that's the part that spins. They create this constant magnetic field. It's always there. And that field interacts with the magnetic field from the stationary part, which is precisely controlled by electricity. That interaction makes the rotor spin, creates the torque, and drives the wheels. It's a proven design, highly effective. It's really what powered the first wave of the EV revolution.
Okay, so if these PSMs are so good, powerful, efficient, the standard basically, then what's the big deal? I mean, aren't those permanent magnets the very thing you mentioned earlier, the source of the problem? What is the real hidden cost? The thing that's got manufacturers, environmental folks, everyone so concerned.
Exactly, you nail it. While PSMs perform really well, relying on those permanent magnets creates several really significant systemic challenges. And these challenges are just becoming more and more unsustainable as more and more EVs hit the road. The big deal isn't just one thing. It hits economics, global politics, and crucially, the environment. So first off, there's the huge material dependence. These magnets almost always use what we call rare earth elements, specific ones, like neodymium, that gives them their super strong magnetic power. And often they add things like dysprosium or praseodymium. These help the magnets work well at high temperatures without losing their magnetism. Now, the name rare earth is a bit misleading. They're not actually that rare in the Earth's crust overall, but finding them in high enough concentrations where it's actually economical to mine them, that's rare. And on top of that, extracting them, processing them into a usable form, it's incredibly difficult, really energy intensive, chemically complex. It's not like digging up iron ore, It's a much, much trickier business.
Huh. So it's less about how much is there globally and more about the sheer difficulty and the specialized process needed to actually get it out, separate it, and turn it into something useful for a motor.
Yeah.
That helps clarify the supply side, definitely.
Precisely. And that difficulty leads straight into the major economic impact. Because it's so hard and costly to extract and process, and because the mining and refining are concentrated in just a few places globally, often really just one or two main countries dominate, these materials are just inherently expensive. But what's even worse for the auto industry, which needs stable, predictable costs for mass production, is the price volatility. It's notorious. I mean, we've seen prices for neodymium swing by 300%, maybe more, in just like 18 months. These huge swings can be triggered by anything: supply chain hiccups, changes in demand, trade disputes, even just geopolitical tensions. Now imagine you're an automaker planning your production years ahead. That kind of wild unpredictability. It's a massive headache. A huge financial risk.
Wow, yeah, I can definitely see that. And I'm guessing, based on how hard it is to get them out, there are probably some pretty severe environmental costs, too. Sounds like it could be incredibly messy. Kind of contradicts the clean image of an EV, doesn't it?
You are absolutely right. And this is where the picture, honestly, often gets quite dark. The environmental footprint of mining and processing rare earths is substantial. In many cases, it's genuinely devastating. A lot of the mining is open pit. That means massive habitat destruction, clearing forests, causing severe soil erosion, just huge physical disruption. But beyond that, the chemical processes needed to separate and refine these elements. They generate enormous amounts of toxic waste. We're talking highly acidic wastewater, heavy metals, sometimes even radioactive byproducts like thorium and uranium. If this stuff isn't managed perfectly, and often it isn't, this toxic slurry can contaminate local soil, rivers, groundwater for decades. It poses serious long-term health risks to nearby communities and causes just irreparable damage to ecosystems. It is, without question, a dirty business. A stark contrast to the clean, quiet electric car it helps create.
That's
Yeah.
Yeah, that's truly sobering, a real contradiction there. So we've got high costs, environmental damage, and I'm guessing there's a layer of global politics in this too. Resource control. Who actually holds the keys to these materials?
Indeed. And that brings us right to the critical geopolitical concerns. The supply chain for these rare earth elements is incredibly concentrated. Right now, one country, China, dominates something like over 85% of the world's refining capacity, plus a huge chunk of the actual mining. This massive concentration creates, well, profound vulnerabilities for car makers and, honestly, for entire national economies around the world. Any political instability, any trade spat, even a natural disaster in those key regions, it could instantly disrupt the supply, affect production lines everywhere. It could potentially slow down the whole planet's shift to electric vehicles. It's a strategic bottleneck, plain and simple, and it poses a significant national security risk, an economic risk for many countries, which is exactly why places like the US and Europe are desperately trying to find alternative supply chains, or even better, alternative technologies that just don't need these materials at all.
Wow, okay, so cost volatility, check. Severe environmental damage, check. Geopolitical leverage and risk, check. All wrapped up in these little magnets inside our supposedly green cars. That paints a really, really compelling why for wanting a totally different approach.
It absolutely does, and this is precisely where ZF's I2SM comes in. I'd call it a direct, elegant, almost audacious solution to all of these problems at once. It's a defining feature, the thing that really sets it apart, makes it revolutionary. It's the complete and total absence of permanent magnets, and therefore absolutely no reliance on rare earth materials. This isn't about reducing them a bit or finding a slightly different magnet. It's a total elimination of that dependency, right, from the core design.
So absolutely no magnets. I'm still trying to wrap my head around that. If you don't have those permanent magnets providing that base magnetic field, how do you even generate the field you need for a motor to work? That's just, it sounds incredible. How did ZF actually manage that? What's the secret sauce?
That is the core innovation, and it's quite ingenious, really. See, instead of relying on a magnetic field that's always there, always on, From permanent magnets in the rotor, whether you need it or not, the I2SM generates its magnetic field dynamically, on demand. It does this using something called an inductive exciter, and this is integrated right into the rotor shaft itself. You can kind of picture it as a small, very sophisticated electromagnetic system built right into the spinning heart of the motor. This exciter creates the magnetic field needed, but only when it's needed. And the truly remarkable part, it does this without any physical contact at all. That's where the real magic, the engineering brilliance lies. It's fundamentally different from a permanent magnet motor, and it's also a significant step up from other magnet-free options out there. Right, let's dig into that a bit more. This contactless power transfer. The key mechanism is the inductive exciter transferring energy to the rotor using electromagnetic induction. So just like it sounds, there are zero mechanical contacts involved in getting that power across.
Okay, now here's where it gets really interesting for me. No mechanical contacts at all. That just sounds like a massive design win. Not just for making it less complex, maybe, but for long-term reliability, too. What exactly does that get rid of? What potential problems does that avoid compared to other motor designs?
Oh, it's absolutely a game changer for durability, for longevity, and just for the overall elegance of the design. First, and this is huge, it means the complete elimination of wear components that you normally associate with getting power to the rotor. You see, many conventional motors that try to avoid permanent magnets, like those separately excited synchronous motors, I2SMs, which we should probably talk about more later, they still rely on physical things like brushes or slip rings. These are mechanical parts, right? Constantly rubbing against each other as the rotor spins, thousands of times a minute. And that constant friction, it inevitably causes wear, it generates heat, it produces fine carbon dust, and eventually those parts need maintenance or they need replacing.
Right, like the brushes in an old drill or something. They wear down eventually.
Exactly like that. The I2SM just completely sidesteps that whole wear mechanism because the energy transfer is entirely wireless through magnetic fields. That translates directly into better long-term reliability, fewer maintenance headaches, which is a massive plus for, say, fleet operators, but also just for everyday drivers over the life of the car. And second, this contactless design leads to a much simpler overall motor architecture. If you don't have brushes or slip rings, you just have fewer moving parts to worry about. That not only makes manufacturing potentially less complex, maybe cheaper, but it also gets rid of the need for complicated seals and housings. Things designed just to keep that brush area clean and dry, protected from moisture or dirt. So you end up with a motor that's inherently more robust, more reliable, and actually cleaner inside. You know that wireless charging pad for your phone?
Yeah.
It's kind of like that conceptually. Energy jumps the gap without any physical connection, just using carefully managed electromagnetic fields. That's basically how the rotor gets the power it needs to create its magnetic field inside the I2SM. It's really elegant, really sophisticated.
That analogy clicks perfectly. Wireless power for the motor's core.
Yeah.
That is genuinely innovative. Kind of mind-bending, actually. But I have to ask, for something so critical in a car, what was the biggest engineering challenge? Making that wireless transfer robust enough, reliable, efficient enough for the tough conditions of the vehicle, constant vibrations, temperature swings, massive power demands.
That's a really sharp question because, yeah, the concept of induction might sound simple, but perfecting it for this specific demanding application, anything but simple. The main challenge is really ensuring highly efficient energy transfer across that air gap while spinning really fast and doing it in a super compact and robust package. So the engineers had to optimize everything. The coil designs, the magnetic coupling between the stator part and the rotor part, the frequency of the inductive field, all to minimize energy losses. They also had to figure out how to manage the heat effectively. Any inefficiency generates waste heat, and that has to go somewhere, especially in a tight space. The solution involved using highly specialized materials, advanced techniques for winding the coils, and really sophisticated power electronics to precisely control that inductive field. They need to ensure consistent, reliable power gets to the rotor under all conditions, from a freezing cold start to driving flat out on a hot day. It's definitely a result of some serious R&D effort.
That makes total sense. It sounds like a huge amount of detailed engineering went into just that one aspect. So, okay, beyond ditching the magnets and beyond this really clever contactless power thing, what else does the I2SM offer in terms of, its actual performance, its practicality? Does it end up compromising on power or efficiency or anything else just because it's built so differently?
Not at all. In fact, in many ways, it actually excels in other areas, too. It really proves that innovation can deliver multiple benefits without forcing a trade-off. Let's talk about its compactness and design flexibility. Because the I2SM has this ingenious, integrated design, The inductive exciter is basically built right into the rotor shaft. It needs up to 90 millimeters less axial space. That's a lengthways. Less space compared to those traditional separately excited synchronous motors, the other main type of magnet-free motor.
90 millimeters. Whoa, hold on. That's, what, almost 4 inches? In car design terms, that sounds huge. What does saving that much space actually mean for the people designing the cars? Especially when everything in an EV chassis seems packed in so tightly already.
It is huge. It's a massive tactical advantage for packaging, for the whole vehicle architecture. That 90 millimeters of extra space along the motor's axis, that's incredibly valuable real estate.
Yeah.
It means more room for other vital things, most obviously the battery pack.
Ah, right. More battery, more range.
Exactly. In an EV, battery size is range, pretty much. Engineers are always fighting for every last cubic centimeter for batteries. So this could directly mean a bigger battery, more range for the driver. But it's not just about batteries. It helps with better weight distribution, which affects how the car handles, how it rides. It gives designers more freedom, maybe create more spacious interiors, or optimize the crash safety structures, or even design completely new kinds of compact EVs without sacrificing performance or comfort. Imagine smaller city cars, maybe compact SUVs, even sports cars where space is absolutely at a premium. It really opens up new design possibilities, and that flows right into performance. Because this is critical, right, for people to actually want these cars. Despite being magnet-free, despite being impressively compact, the I2SM offers power and torque density that is genuinely comparable to, and in some cases, maybe even better than many of the standard PSM motors. So this isn't a compromise. You don't gain sustainability only to lose out on acceleration or capability. ZF has managed to engineer a motor that delivers that instant, strong power, that high torque people expect from a modern EV. But without that Achilles heel, the rare earth magnets, it's a really powerful statement. Sustainable design doesn't have to mean weaker performance.
Okay, that's really key. So it's not just eco-friendly or compact, but it performs just as well, potentially even better than the current standard. That tackles that compromise worry head on. Whenever you hear about a new sustainable tech, you often wonder, okay, what am I giving up here? But it sounds like with the I2SM, you're not really giving up anything in terms of raw power or how the car feels to drive. That's got to be a huge relief, both for car buyers and for the manufacturers.
Precisely. And in some really important areas, you're actually gaining ground, especially when it comes to efficiency, particularly at speeds we use every day. There are two main efficiency gains with the I2SM that are really worth highlighting. First is the elimination of magnetic drag losses. Those permanent magnet motors, the PSMs, they have this thing sometimes called magnetic drag or iron losses from eddy currents. See, even when the motor isn't working hard, like when you're just coasting or driving at a steady speed on the highway, that permanent magnetic field from the rotor magnets is always there. And it induces these little parasitic electrical currents called eddy currents in the stator. This constantly creates a tiny bit of resistance, a bit of waste heat. It's energy loss.
Ah, so it's like the motor's always fighting itself just a little bit, even when you don't want it to, like having the brakes slightly on all the time.
That's a perfect analogy. Exactly. The I2SM, because it only generates its magnetic field when it needs it using that inductive exciter, it completely avoids this parasitic loss. So that directly means better efficiency, especially at higher speeds. Cruising on the highway is a great example, where those drag losses in a PSM can really add up. Bottom line, you can get more range from the same battery charge, and maybe even a slightly smoother, more efficient feel when you're just cruising along.
Okay, smoother, more efficient, especially on longer drives or steady cruising. That sounds like a really tangible benefit for everyday driving. Helps with range anxiety too, I bet. Right. And what was the second efficiency gain you mentioned?
The second gain comes directly from that clever inductive exciter itself, the contactless part. It significantly cuts down on energy losses just in the process of getting power to the rotor. Compared to those traditional SESM motors, the ones that do use brushes and slip rings, the I2SM's inductive system reduces these energy losses in the rotor power transmission by about 15%. That's quite substantial. Think about it. Those mechanical contacts in an SESM, they have electrical resistance, they have friction, they generate heat. All of that is wasted energy. The I2SM just doesn't have those particular losses built in. So more of the power drawn is actually used effectively to create the rotor's magnetic field, and ultimately, more power gets to the wheels. It's another piece contributing to its overall better efficiency. Oh, and we should probably briefly mention cooling, too. Like the best PSMs out there, the I2SM uses highly efficient oil circulation to cool the rotor. This isn't just about stopping it from melting down, obviously. It's critical for keeping performance high and consistent, especially if you're driving it hard or for long periods at high speed. Oil cooling is just way more effective at pulling heat away compared to air cooling. It lets the motor operate at its peak power and efficiency for longer without things getting too hot and performance dropping off. And of course, let's circle back to the whole reason this motor exists. The incredibly important reduced environmental footprint, getting rid of those rare earths and permanent magnets completely. ZF estimates that leads to up to a 50% reduction in the CO2 footprint just during the motor's production. That is a direct, measurable improvement, a real step towards truly sustainable electric mobility. It fits perfectly with the bigger goal of switching to EVs. It reminds us it's not just about zero tailpipe emissions, it's also about how the vehicle is made, making the whole life cycle cleaner, from cradle to grave.
50%. Wow, that is absolutely massive. So it's greener right from the start, from its manufacturing, and then it's more efficient during its life. That's a really powerful combination. And you mentioned something earlier about voltage flexibility. What's the deal with that? Does it give car makers more options? Does it tell us anything about what kind of vehicles this motor is aimed at?
Yes, exactly. That's another key aspect that really shows how versatile and forward-thinking the design is. The motor is engineered to work seamlessly with both 400-volt and 800-volt electrical systems in the car. Now, for those higher performance 800V systems, which are becoming more common, especially in premium EVs and ones that charge super fast, the I2SM uses advanced silicon carbide power electronics. Silip chips are a big deal in semiconductors. They're much better than traditional silicon for high power, high frequency stuff like this. They can handle higher voltages, higher temperatures, they switch on and off much faster, and they do it with way less energy loss. So they're perfect for the demands of an 800V system. Having this built-in voltage flexibility gives car manufacturers huge design freedom. They can adapt it easily. Why care about 800V? Well, primarily it enables ultra-fast charging. We're talking adding hundreds of miles of range in like 15, 20 minutes at the right charger. Makes charging stops feel more like a quick coffee break.
Okay, so 800V is key for tackling charging times.
Absolutely. And it also generally allows for higher efficiency, especially in really demanding situations or in high-performance vehicles where you need sustained high power output. So whether a car company is designing a standard family car, a high-performance electric sports car, or even maybe a hard-working commercial van, the I2SM offers the versatility they need. It can fit different market segments, different performance targets. It really makes it a kind of modular solution for all sorts of electric vehicles. Okay, so to really grasp just how much of a leap forward ZF's I2SM is, it's helpful to compare it directly with that other type of motor that also avoids permanent magnets, the separately excited synchronous motor, or SESM. Now, SESMs definitely solve the rare earth problem, right? They generate the rotor field electromagnetically too. But the I2SM is really like the next generation. It manages to engineer out some of the drawbacks that traditional SESMs have.
Right. So it's not the only way to go magnet-free, but it sounds like ZF basically took that concept and found ways to make it fundamentally better. Where does the I2SM really pull ahead? What are the key differences that, say, a car manufacturer or even just a curious driver like me should really understand?
That's a great way to put it. Yes, they're both magnet-free in the permanent magnet sense, but how they generate and transfer power to create the rotor's magnetic field, that makes all the difference, especially for things like long-term reliability and overall efficiency. Let's break down a few key points. First, axial space. We already touched on this, but it's worth repeating. The I2SM is incredibly compact. It needs up to 90 millimeters less length than a typical SESM. Why? Because a traditional SESM needs physical space for its excitation system, those brushes and slip rings we talked about, plus all the housing and cooling needed just for those parts. That adds length, makes it bulkier. The I2SM, with its integrated, contactless inductive exciter, just doesn't need that extra external hardware. So big win for packaging, especially as cars, even EVs, trend towards being more compact. Second, and this is probably the most crucial difference, how energy gets to the rotor. The I2SM uses that clever inductive contactless method, wireless power basically. No physical connection, no friction, no wear on the transfer itself. An SESM, on the other hand, relies on mechanical brushes or slip rings. Think of little spring-loaded blocks, usually carbon, pressing against spinning metal rings to conduct electricity.
And those mechanical contacts, that's where things start to wear out over time, right? That sounds like where reliability issues could potentially creep in with SESMs.
It's exactly. Which brings us to point 3. Mechanical wear. With the I2SM, in that power transfer part, it's simply absent. No brushes, no slip rings, nothing rubbing together constantly to generate friction, heat, or that fine carbon dust. So virtually no mechanical wear in the excitation system itself. In an SESM, though, those brushes and slip rings are wear items. by definition, over time they degrade, they wear down. That carbon dust they create can potentially cause electrical issues if it builds up, and eventually they will need maintenance or replacement that adds to the lifetime cost of owning the vehicle and potential downtime, which is a big deal, especially for commercial fleets. So the I2SM just seems fundamentally more reliable and lower maintenance in that respect. Then there's energy loss. Remember we said the I2SM's inductive system cuts energy losses in getting power to the rotor by about 15% compared to SESM's. Those mechanical contacts in SESMs, even when they're brand new, they inherently have electrical resistance, they have friction, both create heat, both are wasted energy. The I2SM's contactless transfer avoids those specific losses. So it's inherently more efficient at the job of energizing the rotor, which contributes to better overall efficiency, better range. For cooling, while both motor types can use efficient methods, the I2SM, like top-tier PSMs, is specifically designed for that highly effective oil cooling of the rotor, ensuring stable, high performance even when pushed hard. And finally, let's think about the overall environmental impact. Yes, both I2SM and SESM get rid of the rare earth magnets, which is great. But the I2SM, because it eliminates those rare earths and is optimized in its overall design and manufacturing, is projected by ZF to have up to that 50% lower CO2 footprint during production. And SESM, while good on the rare earth front, might still have a higher overall footprint. Maybe its other components are less optimized, or maybe you factor in the environmental cost of producing and eventually replacing those wear parts like brushes over the vehicle's lifetime. What's really quite brilliant here when you step back is how ZF seems to have cherry-picked the best ideas from different motor types. They took the high performance and efficient cooling often seen in PSMs, they took the magnet-free concept from SESMs, and then they meticulously engineered out the main drawbacks. They got rid of the reliability issues of brushes, they boosted efficiency with contactless power, and they delivered it all in a super compact package without losing power. It really feels like a significant leap forward, combining the best traits into one optimized solution. So if we zoom out now and connect this to the bigger picture, the I2SM isn't just, a cool new piece of hardware. It feels like a really profound strategic step for the whole electric mobility world. It represents a concrete move towards a future for EVs that's genuinely sustainable, scalable, and robust globally. This technology directly helps create electric motors that are more sustainable, more efficient, and more compact, all without asking for a performance trade-off. By completely cutting the cord, severing that dependence on critical problematic materials like rare earths, the I2SM tackles major worries about whether we can even make enough EVs for everyone affordably and responsibly. Just think about it. The world is shifting to EVs incredibly fast. We're talking potentially tens of millions of them being made every year within the next decade or so. If all those cars used traditional PSM motors, the demand for rare earths would just explode, skyrocket. That would inevitably mean even higher prices, much more environmental damage from digging up more land, and probably increased geopolitical friction as countries scramble for those limited resources. The I2SM offers a clear, practical way to sidestep a lot of that impending crunch, which is absolutely vital if we want mass adoption of EVs worldwide. It basically removes a huge potential bottleneck.
Yeah, that makes perfect sense. This really does sound like it could help make electric cars not just a niche thing or something you have to compromise on, but a truly accessible, much less impactful solution for everyone, everywhere. Which, let's be honest, is what we all hope for, right? A cleaner transport future that doesn't just create new problems somewhere else down the line.
Exactly. And from ZF's side, this isn't just some interesting lab experiment or a concept car gimmick. The I2SM technology is actively being pushed through advanced development. They're aiming for production maturity. That means tons of rigorous testing, validation, figuring out how to manufacture it efficiently at high volumes. And importantly, it's designed to slot right into ZDEF's wider eDrive platform. This is their sort of modular toolkit for electric powertrains. That modularity means car manufacturers get amazing flexibility. They can choose the voltage 400V or the high-performance 800V. They can spec different power and torque levels to suit whatever vehicle they're building. What that means practically is car companies won't need to totally re-engineer their entire vehicle platform just to use this new motor. It's designed more like a drop-in option within ZF's adaptable system. That makes it much easier, much faster, much more cost-effective for them to actually adopt this innovative, sustainable tech in their upcoming cars.
So it lowers the barrier for them to make the switch.
Precisely. It smooths the path. crucial for getting it adopted quickly across all sorts of vehicles, passenger cars, SUVs, even light commercial vans. It helps OEMs embrace magnet-free power without a massive upfront redesign cost or delay, which naturally leads us to the big questions. For us, and for you listening, how quickly will we actually see these kinds of magnet-free motors, like the I2SM, becoming common, moving from the R&D labs onto the roads we drive every day? And maybe even more exciting, what other innovations could this fundamental shift unlock, not just in motors, but maybe in the whole EV ecosystem, or even beyond that, in energy systems?
Wow, what an incredible deep dive. It is genuinely amazing to see how smart engineering, real innovation, can tackle such complex, systemic problems, making electric vehicles not just efficient, but actually better, more sustainable, less dependent on materials that cause problems halfway around the world. You've really helped unpack this for us, taking us from that critical why we need something different, through the really intricate how ZF pulled off this elegant solution, and then exploring the really profound so what for our future. It feels very clear this isn't just a small step, it's a foundational shift in thinking about the very heart of an electric vehicle.
It's been my pleasure. And you're right, this technology, it doesn't just solve a supply chain headache or an environmental issue. It genuinely pushes the boundaries of what we thought was possible in electric motor design. It really shows we don't have to just accept the current limitations or stick with the status quo just because it's familiar. So as you think about all this, here's maybe a final provocative thought to chew on. If we can re-engineer something as fundamental as the electric motor, make it free of these critical damaging materials, and potentially even improve its performance, what other parts of the EV supply chain might be next? Could we see similar revolutions in batteries, power electronics, even the materials used for the car's body? What completely new opportunities might that unlock? For entirely new vehicle designs we haven't even imagined yet, for totally different manufacturing methods, or maybe even for innovative energy systems that are truly sustainable from end to end, completely reshaping our industrial impact.
Powerful questions indeed. Lots to think about as we look ahead.
Absolutely. And if you enjoyed this deep dive into ZF's I2SM motor, if you found these insights valuable, please do make sure to hit that like button and definitely subscribe to the channel. That way you won't miss our next exploration into more fascinating topics like this. We're always digging deeper.